Okay, so we are going to look at Java non-blocking I/O. Okay, and what I've done in the past is point students to, this is a Java API. Any Java API is well discussed on the web, and I found, I think, the most popular tutorial on it. I understood an I/O from that tutorial, and I did the assignment myself based on the tutorial. And like I mentioned last time, I asked the students also to use that tutorial. And what the tutorial does is tell you how to build the following distributed application. It's an application in which there is a server that can talk to an arbitrary number of clients. Each client can send a message to the server. The server sends the message back to the client. This is classic. When you're looking at distributed computing, the tutorials that are written tend to create echo servers. Okay, so this was an echo server, and it echoed only one message. So after the message was echoed, the client disappears. Okay, that was the tutorial. So it lets you use an I/O to send messages, receive messages, and so forth. The assignment requirements was similar. There was a server that would talk to multiple clients. Clients would send messages to the server, and the server wouldn't really interpret the messages like the echo server. But what it did was that it didn't just bounce the message back to the client. In fact, in the default mode, it sent the message to the other clients and not to the client that sent the message, not to the sending client, but to the other clients. Okay? And a difference also was that you could send an arbitrary number of messages to the server and get them relayed. Okay? So the server was a relaying server. Your assignment description also has an option where the messages are echoed back to the client. Okay? And anybody who's read the assignment, do you know what feature in the assignment requires an echo back? Nobody's got that far? Yeah. Beautiful. Atomic broadcast. Okay. So, it's not that different. It was different enough that students learned from it. So that was good. But also it was different enough that a lot of students have trouble. Okay. And, I don't exactly know what the causes of the trouble were. But I can tell you what I liked about the assignment and what I didn't like, and what I didn't like perhaps caused problems. That the assignment explained an I/O and its limitations well. And it had an implicit application architecture, which, if you could make it explicit in your head, was a good architecture. Okay, so I like that general architecture. So, but some students had trouble understanding how it was to be modified to the new application. So, when you have a problem, you often go to Stack Overflow, you get a solution, and you change it to your problem. Sometimes you don't have to make any changes, sometimes you have to make many changes. And often you make the changes without really understanding what that code is doing. Okay? And if you took that approach, students had trouble morphing it. There was a design pattern, but it was not explicit not made explicit in that tutorial, so people had trouble getting it. And the reason why Stack Overflow is used so much is because certain patterns have not been converted into abstractions. Okay, when you have a problem and you go and look at the solution to another problem, that means there's some common solution to both the problems, because that's the reason why that solution works for you. But that solution is not an abstraction. Okay, it is a piece of code that you morph. Okay, so it's like doing assembly programming, seeing how a loop is done, and then changing it to your needs rather than having a loop abstraction. Okay, seeing how you can simulate an array using multiple words rather than having an array abstraction. Okay, so as a fix to this problem, I figured it would be nice to have an abstraction and to make the design pattern explicit. So that's the goal behind what I'm going to do in the next 2 weeks, perhaps. Okay, so rather than rely on the tutorial, we're going to look at it from first principles, and hopefully that will be that'll have use. You always have the rocks tutorial. I'm not saying it'll be a better explanation, but there'll be an alternative explanation, and it can't hurt being an alternative explanation. Okay. Now, it's not that I didn't do an I/O in class. And it's not that we don't have other lectures that will address that. The way I like to understand something is and the way I think people generally understand is to look at the diffs between systems. You don't want to go and look at sockets and NIO and RMI and pipes and study them as point systems. You want to say, okay, they are in some design space. Here are some dimensions. These are decisions they took that were same. These are the decisions that they took that were different. So what are the issues on which you have to take decisions, and what are the various approaches? Once we get that design space, we can go and put this system here and this system here, and that contributes much more to understanding. Okay? So it's like looking at all the sort routines and not understanding them from first principles, but looking at the difference among the sort routines. Okay? But for now, so this is the first system we are looking at. We'll focus on a point. I'm not going to relate it very much to other systems, other approaches. I'm going to relate it a little bit to sockets because it was derived from sockets. But otherwise, we're going to just focus on that particular point. Okay? You want the design space later? There are lectures, okay, that are recorded that you have. Questions so far? So there are really three questions that we have to answer. Okay? NIO is something that I'm using for distributed computing. Distributed computing involves processes talking to each other, so it involves inter-process communication. Okay? And somehow this I/O has to do with inter-process communication. So let's try to understand what I/O really means. Okay? That's something you learn in CS1, but we'll look at it a little bit more deeply here. Try to see what the relationship between I/O and inter-process communication is, and then we look at what non-blocking really means. Okay, so we'll divide this into three parts. Okay. So I/O, well, we can think of there being one. You can think of this as being two objects or one object, a display object and a keyboard object. We'll just treat them together as one console object. Okay, and we'll use a very simple form of I/O, just character I/O, and we'll say there's a console object that defines two methods, put a character and get a character. Okay? So let's try to understand what this really means. What does get a character mean, and mean exactly from an... So what does it exactly mean? Yeah.
Maybe like get it from user input? Like
Get,
or something?
okay, so return a value that the user input. Okay, that's good. And do you want to elaborate more on get? So
Like maybe if there is no user input, we wait until the user actually puts something in.
if there is no user input, block. Okay. Now, those of you who studied operating systems, you know what it means to block. You get put away from the ready queue to a wait for user input queue. Okay. And so you, meaning the program, the process, the thread that called get, put in that queue. How do you get unblocked? So somehow when input occurs, you get unblocked. From an OS point of view, what's really happening underneath? An input interrupt occurred. That executed an input interrupt routine. What thread does that input interrupt routine execute as part of? It's certainly not the thread that was blocked. Some other thread. Sorry?
Like whichever thread is managing input.
So maybe there's a dedicated thread in the kernel that manages input, or maybe whichever user thread is executing at that time. Okay? Both approaches are taken. So there's some blocking in get, potential blocking. That's the key here. We talked about this last time a little bit. What about put? So put is put a character on the display. Any blocking going on here?
Get often uses reachable buffers, creates some sort of buffer injection. So if that buffer is full, put blocks in some other space to insert the character into the buffer.
So you're going to put, you're a thread. The thread's going to asking for the character to be put. Is the thread that's going to actually put the character on the device register? Is that the thread that's going to do it? you're right. When some kind of, so there might be a buffer, and the buffer might be full. So that buffer gets emptied when?
Get called.
No, get is reading from the user input.
Okay.
So I'm not putting the get doesn't return what I put. The get returns what the user input.
Put will empty the buffer. It's consuming from the buffer that gets putting into. And then
So it's putting into some buffer, and that gets emptied by?
put some thread that's reading. And, like, we have some dedicated consumer thread that's reading from that buffer. It'll pass that on.
Okay, and how does it get put on the device? What code, So it just puts it on the device register? So there's the device register that it has to go on. So does the thread that did the put actually put it on the?
Oh no, it has to make a system call.
It makes a system call. The system call now, let's say, is executing as part of this thread. I'm thread T1. I made a put call. Let's go and look at get again, just to make it clear. In the case of get, there was some thread T1. It wanted a character. If the character was already there, it returns with the character. Okay? If it's not there, it gets put in a queue. At some later time, a character gets put in. When a character gets put in, some thread T2 executes, consumes the character from the device, unblocks T1 with the character. We get that? Now let's look at put. So what did that thread T2 do? There was a device register that had the character that the user input. It read that character from the device and put it in some kernel space that thread T1 could access. Okay? Now let's look at put again. Some thread T1 says, I want to put a character. Okay? It's not as if this character is going to be read by a get. It's going to be put on the console. Okay? So really these are two different devices, independent devices. I've just clubbed them together. So it goes and says, I want to put a character. There is a device register to which it can write. Once it's made a system call, it's in kernel mode. There is a device register that it can put the character on. And I'm hinting it doesn't quite do that. Yeah.
Does it also put it somewhere in the kernel space before it gets transferred to the...
So it puts it somewhere in kernel space, and that I'm hinting there, which then gets copied onto the device register. But why not put it directly in the device register? Yes. The device register will not be available if it's being, sorry? If it's being used by somebody else, it's always used by the device. So, but for some reason that device register is not ready to be put into. And why would that happen?
Maybe the device hasn't consumed the last character yet?
The devices may be working slower than the CPU. Devices typically work slower than the CPU. Okay? So maybe the last character has not been consumed. So we don't want to overwrite the character and overflow that device register. So when should it be consumed? How do we know that the device is ready, has consumed the previous character?
I guess we just have some indication that it's empty.
And what is the technical term for such indications from the device? Indication of the device's CPU are called interrupts. Okay? So in the case of get, the input device, whenever it has a character that needs to be consumed, it goes and interrupts the CPU saying, I got a character for you. In case of the output device, whenever it has finished the last output and the register is ready to write, it interrupts the CPU and says, I'm ready to be written again. So the output is written not by the call to put, but by the output interrupt routine. So yes, indeed, put will go and put this character somewhere in kernel space. Later, an output interrupt routine will occur, which will go and consume it as part of some other thread. T1 put the character, some other thread T2 will be executing when the output interrupt occurs and consume the character. Okay? So this code that's running in the kernel is called the device driver. Okay, you guys know about device drivers. You install them sometimes. Interrupt routine is part of the device driver, and the routine in the kernel that serves your put and get, that went and read from the device register and put it in the kernel space or vice versa, is also the device driver. Okay. Now that you've sort of seen what's happening here, so in your OS classes, those of you who took OS, did you guys actually look at this kind of interaction, this depth? Output interrupt routines, input interrupt routines? Maybe, okay. What's a problem that you looked at that is an abstract problem that is being manifested in both of these cases? The producer-consumer problem, okay? You guys have probably seen zillions of ways of doing the producer-consumer problem. Here is actual producer-consumer at work, okay? So we really have two agents, application and device. They're working concurrently. They're working at different rates. And whenever they're working at different rates, when you have two agents that need to exchange information, they're working at different rates, you have a bounded buffer or some buffer in between. And one agent produces information that goes into the buffer, one agent consumes it. Okay? And the production and consumption may both involve blocking. Okay, we saw that get blocks because it's consuming, put blocks because it's also consuming, because that device register is full and it can't go any further. Okay? So let's look at it as a producer-consumer problem. Okay? And in fact, we look at IPC also as a producer-consumer problem, as we'll see later. So the producer-consumer problem is going to be extremely important for this course. Okay? So what really happens is that put doesn't wait for each device at each time. It doesn't wait for the device register to be really free. It puts it in a buffer in the kernel. Okay? If that buffer gets full, then it will block. Otherwise, there can be 1,000 characters pending in the kernel. Doesn't matter. We don't have to block put for each device output. And what the TTY output routine does, which is the consumer, it goes and empties the buffer. Okay, and it empties it at its rate, and so that's what's happening. Upper half. So the device driver has got two halves. One is the half that's putting things into the buffer, and one is the half that is consuming things from the buffer. Okay, so when you think of a device driver, you get both parts, and one part executes as part of the thread, so user thread, that makes requests to the kernel, and one part gets executed as part of the kernel thread. Okay, and it enqueues the printed characters in a buffer. Okay, and there's also this is not the device register. The device register is a separate thing in the device. Okay, and what the consumer does here is read things from the output buffer, and at the correct times output things, put things in the device register. Okay, lower half executes in the interrupting thread. Okay, and consumes next character and writes it to the device register. So this consumption occurs only when the device is ready to be to consume. So when it's ready, it goes and takes the next character and puts it in the device register. Okay. Questions? Okay. And so the question is, when does the output device really interrupt? Every time it consumes a character, it interrupts, saying, I just finished consumption. Okay. It also interrupts whenever the device interrupts are, if you clear the interrupts and then enable them again it goes and interrupts at that point, saying, okay, I can. And you'll see why that's important later. Okay, so you can disable and enable interrupts. Each time you enable disabled interrupts, an output interrupt is posted right at that point. Okay, and we'll see that's important later. What about input? Well, we have the dual situation. We now have an input buffer. Okay, so the user may be typing away for a process, but the process may not be ready to consume things. And do we have a phone here or what? Why? It says automatic shutdown. Doesn't like my lecture. So, okay, thank you. I was in another class this morning, and I heard a similar sound. It was somebody's mobile phone ringing from previous class, so I thought maybe it's the same thing. Okay. So the dual situation. Now you have the upper half being the consumer of information. It's doing a get, and the input interrupt routines are putting things in the buffer. It may be the case that the user is typing away. You can type ahead, and there is no process to consume the characters. Okay, so the characters have to be buffered somewhere. That's the input buffer, and it puts it into. It's a producer, and the get goes in, consumes from that. Okay, so we have the producer-consumer problem again at work. Okay, so the upper half consumes characters, and reads device register and puts in read buffer. Okay. So each time a new character is put into the register, the device will interrupt. Okay, so whenever on input, it will interrupt. So now let's look at the blocking semantics. The put will block when we have an output buffer, so it will block when the buffer's full, right? Now we know that the lower half has to block if the buffer is empty, right? But does it make sense for an output interrupt routine to block, for an interrupt routine to block? I'm kind of hinting that it doesn't make sense for an interrupt routine to block. Why not?
It's handling the interrupt or like generating stuff, so it's what's signaling the other bit blocking.
So that's right. You know, if the other process is waiting for, waiting on a full buffer, it goes and says, hey, you've got a new character now. So it's signaling, that's true. But we know that in the producer-consumer problem that you studied in operating systems, both parts can block. Yeah.
The interrupt handler is operating with interrupts disabled. So if you want to block it, you either have to have some policy to enable interrupts beforehand, because if you don't, your whole device is dead.
So your whole system is dead because you block all interrupts. Okay. Why do you block all interrupts, by the way, when you are executing an interrupt routine? To make it atomic. Excellent. Okay, because you're in kernel space, you're accessing concurrent data structures. If another interrupt routine executes at the same time, you're going to. Okay. So also, if you start blocking the interrupt routine, then those things will get cascade. If the user is inputting characters, outputting characters, they'll cascade. And look at, just imagine that your thread asked for a character to be put, and my thread happened to be the one executing when an interrupt occurred. And now my thread is blocked. So it just seems wrong from so many points of view. Okay? So interrupt routines cannot block, whether they're input interrupt routines or output interrupt routines. So we've got a little tricky situation here. Device register might get full. Okay, so if you blocked, a new character will be overwritten, so the previous character will not be read. Often interrupts disabled while they are executing to ensure atomicity. Okay, so you go and disable clock interrupts, you disable all kinds of interrupts, so no context switching will take place, you lose track of time, and blocked routine can starve or delay threads. Okay, so the TTY output driver cannot block, so what should it do? The TTY output character just output the last character in the buffer. Okay, it emptied the buffer one by one, and it just output the very last character. And now it goes and posts an interrupt and says, I'm ready for another character. And there is no other character. So it returns. Now another user goes and puts a character into the buffer. How do we trigger an output interrupt to consume this new character? See the problem? If I already have a full buffer, no problem. Okay, I went and printed out 10 characters. Okay. And somehow interrupts got started up. And interrupt number 1 consumes the first character, interrupt number 2 consumes the second character, till we get to the 10th character. It consumes the 10th character, all 10 characters out. Now after 10 minutes, I go and put another 5 characters. How do I trigger output of the first character? Because there's nobody waiting. I could signal somebody if they were waiting and saying it's a non-empty buffer now. Okay? But there's nobody waiting.
You can poll, but so you don't want to do that.
We don't want to poll. I told you a characteristic. Enabling, disabling interrupts.
Oh, we re-enable after we.
So,
Yeah, after we've done put everything in the buffer, like once our interrupt's done, we always re-enable. Like once we've done whatever's been disabled, we always re-enable before we exit. That way.
so let's get it right. I output 10 characters. The 10th character has been consumed by the output interrupt routine. What happens at this point to interrupts? Interrupts are enabled during the 10 characters being output. After the 10th character's output, what happens to the interrupts?
Disable.
So you disable them. Now later I go and output another 5 characters. What happens when I go and put the first character in?
You can enable that.
Sorry?
You enable.
You enable interrupts, and interrupt routine will start, and they'll start the process. So that's a signaling that's happening. Okay? And I remember I took all these OS classes, where we never studied interrupt routines, and I started writing my first device driver, and I was actually copying a device driver from one machine to another machine, and I couldn't understand what was going on there. So I went to my advisor and said, what's going on here? And he said, oh, that's frobbing. So he called this term frobbing. I haven't seen this term later again, but this is what was going on, which was sort of a subtle detail, but it was subtle enough to confuse me. So, so that's what goes on. Okay? After outputting the last queued character, the interrupt routine will find the output buffer empty. It won't wait. So what it is, it disables interrupts. So upper half enables interrupts when it writes to the output buffer. Okay, and this kind of signaling we'll see when we talk of interprocess communication. This is all going to be fundamental. You're saying, what's this got to do with distributed computing? Okay, this has got everything to do with distributed computing. Okay, questions? So enabling disabled interrupt causes an output interrupt to be posted. Okay, now let's try to face the problem that TTY input driver cannot block. Okay, so remember the upper half, yeah.
So quick question. So if operating systems when you're writing to like a buffer, you disable interrupts and then write to the buffer, so that no one else can also write to the buffer, and then re-enable interrupts. And now you're saying we're
So you're saying, okay, we just heard before that when an interrupt routine is being executed, interrupts are disabled, right? And then we also talked about disabling and enabling certain kinds of interrupts in the interrupt routine. So what's really going on is the following. When you disable interrupts in general, you're saying, I'm not listening to the interrupts. You're not stopping the devices from saying, I've got an interrupt. You're just saying, I'm not going to listen to them. That's one thing. When you enable and disable specific device interrupts, you're saying, you can speak. Okay? So the question is whether you allow the devices to speak or not. And the other question is whether you listen to them. So when you disable interrupts in the and while doing a kernel routine, you're just saying, I'm not going to listen to anything that's being posted. So devices are posting interrupts. You're just not listening to them. Okay, so there's something called cycle stealing where you actually go after each cycle and go and check whether there are interrupts or not. You don't do that checking. so that you don't execute the output interrupt routines. But when you disable output interrupt, you're saying don't even put an interrupt signal on the bus. So that's a status in the device. That's a flag in the device. The other flag is in the CPU.
So this is on the device?
So which one? So right now, the one
we just did.
on the device,
Okay.
saying, hey device, don't even post. Don't raise your hand. Okay? Okay, very good question. Okay, now what's happening is we know that in the get routine we're consuming from a buffer. Okay? That buffer is being populated by the input interrupt routine. And if the buffer is empty, that means the user has put nothing, we will block. No problems. We can let the thread block. But the producer cannot block if the buffer is full, because the producer happens to be an interrupt routine. Okay? So, can you see that? We solve the problem for the output case. Can we solve the problem for the input case? What's really happening? The user is typing a lot and the process is in some loop, not even reading. We can't really solve the problem. Okay, we can't make this particular thread block, and we can't force somebody to consume it. So if you really type a lot, type ahead, and the buffer gets full, what the operating system does is start beeping at you, saying, hey, you're inputting, nobody's listening to you, stop inputting. Okay? So there's a beep character that the Unix kernel will output if you go ahead too much. So that's what happens. Okay? Echoes a bell character to the user to not type anymore. Okay? And you guys work with fast CPUs, you have never seen this, but having worked with old computers where I could type faster than the CPU was processing, I've actually seen this. So what you have is not a classic bounded buffer. Okay? Bounded buffer, the classic bounded buffer object makes both the producer and consumer wait. Here, the one half doesn't wait, depending on whether that half is executing in the upper half or lower half. Okay, so the lower half doesn't wait. So output producer can synchronize, producer waits but not consumer. Input consumer synchronize, consumer waits but not producer. So, and there's actually a data type in Java that you have to use for assignment 1 called the array blocking queue. Okay, and you have a selection thread in your project that's like an interrupt routine. That selection thread is not supposed to block. So the selection thread will be executing non-blocking operations, and your client threads will be executing blocking operations. And this particular data type has got a put and a get take. The put is a producing blocking put. The get is a blocking consuming get. And if you don't want to block, you do an add or a get, and you can go and check the queue to see whether it's empty or full before doing this, and you can go and print out an appropriate error message if the condition for your precondition for your method is not met. Okay, so you need to in your assignment use both sets of routines, because a very similar process occurs there where you don't want the selection thread, which is like an interrupt thread, to ever block. Okay, when you start to that, when you get to that, you'll understand, and by the time you finish this set of this material, you understand exactly what I'm talking about, what a selection thread is and why the rules. Okay? Questions? Okay. So the put and get take methods are synchronizing methods, and the add and get and size methods are non-synchronizing. Okay, so we understand now how the console works. There's really two bounded buffers that are independent, okay, of each other. So there's really two devices, and we are either consuming or producing characters into the bounded buffer. So it's a producer-consumer problem. So we have an understanding of I/O, okay, from an implementation point of view. Now, what does I/O have to do with interprocess communication? Okay. So let's try to answer that.